some terminology, these original states, these states are called the uncoupled states. You're not coupling in a non-trivial way. You're not entangling angular momentum and spin. It's just a product. So these are called uncoupled states. And in the uncoupled states, all the uncoupled states are eigenstates of L squared and of S squared. They're not eigenstates of L dot S, and they're not eigenstates of J squared, which is the same thing. But these uncoupled states are eigenstates of L squared and S squared. So some remarks. The uncoupled states, these are the original L, M, S, MS, are eigenstates of L squared and of S squared. Okay. Any linear combination of the uncoupled states will, and they are all more important than that, all of them have the same eigenvalues. Eigenvalue here is h squared, L times L plus 1, which is 2h squared, because we're working just with L equals to 1. And S squared, eigenvalue is h squared, 1/2 times 3/2, so it's 3/4 h squared. So they're all degenerate eigenstates of L squared and S squared. So any linear combination of these uncoupled states, linear combination of the uncoupled states, are still eigenstates. Eigenstates of L squared and S squared. But what you gain by selecting peculiar linear combinations is that you will manage to make them eigenstates also of J squared, we claim. So also eigenvalues of J squared. So peculiar linear combinations will be eigenstates of J squared or L dot S, which is the same thing up to a constant, because they're anyway eigenstates of L squared and S squared. So the uncoupled states are just one at a time. Linear combinations, we call them the coupled basis. It's like an entangling of angular momentum with spin. And the coupled bases are the ones, those peculiar linear combinations that will also be eigenstates of J squared. So we will try to figure out what are those coupled states, those interesting states that are eigenstates of J squared. So a few more remarks. Recall the nature of L squared. L squared commuted with any Li. S squared commuted with any Si. And any Li with any Sj commute. They act even on different state spaces. That's why they commute. Because Li, after all, means Li tensor 1, and Sj means 1 tensor Sj, and then you multiply them and you get the same thing, independent of the order. So they commute. So you should remember this, and this is something nice to think about, that L squared is called the Casimir operator. It commutes with everything. Why? It commutes with Li, it commutes with Si's. So It commutes with anything that is built with L and S. It will not commute with things that are not rotational invariant, but it will commute with any Li or Si operator or thing constructed from them. So L squared commutes, L squared and S squared commute with anything built from L vector and S. Commutes with anything that you build with those things. So if we're now looking back at this matrix elements and think a little what's going to happen here. So let's anticipate what's going to happen here. And if you have a matrix element I delta H J, what's really the meaning of this matrix element? How is it computed? Well, matrix element means overlap of states. And what are our states? Well, a typical state I, for example, is this psi1 of R times some state, I will call it I underbar, that is going to be some combination of this L and S parts. Remember, so a general state is a radial part and then something to do with L and S parts. This is the radial wave function, the angular wave function, and the spin wave function. So when you're doing a matrix element here, of what? Well, delta H schematically is a number. We have it in the blackboard at the beginning, top leftmost, 1 over R cubed times an L dot S. And then, if you want to think of I delta H J, what do you have? Well, you have to do the bra here and the inner product, so it involves the integral r squared dr over the radial part of the wave function, psi1 star of r, psi1 of r, and since you're integrating r, it involves a 1 over r cubed. And then it has the other part, the I underbar, the LS operator, and the J underbar. So the key thing that is going to happen now is that in the basis of eigenstates of J squared is the same thing as the basis of eigenstates of L dot S. If we select those i's and j's here to be eigenstates of L dot S, this matrix, by definition, is diagonal, and we've solved our problem. So independent of what's happening here, this could be written as the radial expectation value of 1 over R cubed in the L equal 1 state, with n equals to 2, times I L dot S J. And if these states, I underbar and J underbar, are eigenstates of the total angular momentum, this will be diagonal. We will be in the situation we wanted in this blackboard over here, where the perturbation is diagonal. And therefore, this will be the energy corrections. This will be the energy corrections if you take I and J to be the same. This number will be the energy corrections. So I could say here in the basis of LS eigenstates this expectation value of delta H is diagonal. So last thing we want to talk about now is the set of commuting observables. Whenever we have a quantum problem, we want to know what is the maximum set of operators that can be simultaneously diagonalized. And that tells you a lot of information about the problem. So let's review what this commuting set of observables is. So complete set of commuting observables. So if we have the hydrogen atom to begin with, the unperturbed hydrogen atom, unperturbed H atom, we have a Hamiltonian H0 square, H0. And what else have we learned is commutes with this hydrogen atom is the angular momentum. It's a central potential problem. So you have L squared and LZ. And this is a set of commuting observables. And the basic reason is that you can show that the hydrogen atom commutes with any angular momentum operator, the Hamiltonian commutes, and therefore this thing commute. Remember, if any Li commutes, L squared will commute, and LZ commutes with L squared, and we cannot add more operators because if we add an Lx, for example, this would not commute with LZ. Now, if we include the spin of the electron, this can be enlarged to H0, L squared, LZ, S squared, and SZ. And the reason is that the original Hamiltonian knows nothing about the spin, so it commutes with it. And as you've seen, L's and S's commute with each other. So this two commute with this, two commute with this, and they commute among themselves. So by the time you add the electron spin, you add the electron spin, the complete set of commuting observables has become a little larger. Now, let's consider include now LS coupling. So the Hamiltonian is not anymore H0, but is H prime. That's a full Hamiltonian. So what can I include here? Well, can I include all of the things that I have here? Let's put L squared and LZ. Well, Li, H prime now has H0 plus L dot S. So I have to ask, L squared did commute with H0, but does it commute with L dot S? Actually, it does. But any Li with L dot S is non-zero because we have an Lx. Well, the Lysy term here will not commute to give 0, nor the Z1, and they will not cancel. So Li doesn't commute with L dot S, and L dot S is part of H prime. Therefore, you cannot put Lz here. So I'm sorry, we can keep L squared, because L squared commutes with any Li with any Si, so L squared does commute with L dot S, but Lz doesn't. S squared is good too, but Si does not commute with L dot S. So you have L squared, S squared, and we seem to have run into trouble. But can we add something else? And the question is, maybe I can add j squared. Can we add j squared? Well, j squared is the same thing as L dot S for all intents and purposes, because it differs from this ones by this thing. So let me go slowly through this. J squared, how about j squared with h0? Does it commute j squared with h0? H0 was the original Hamiltonian. J squared is built with Li's and SI's, doing sums and products and all things. But the Li's and SI's commute with H0. So anything you build with Li's and SI's will commute with H0. So this should be 0. How about J squared? Does it commute with the part of H prime that is extra? Does it commute with L dot S? Well, that case is also simple, because you should remember that the L dot S is given by this. So j squared with L dot S is the same square as j squared with 1/2 of j squared minus L squared minus S squared. And j squared commutes with j squared. J squared commutes with L squared, because L squared commutes with anything built out of L and S. The same S squared commutes with j squared. So this is 0. So indeed, j squared commutes with H prime. And by the same reasoning we said, j squared commutes with L squared and with S squared. So yes, we can include j squared here. That's a good thing. So we do add it. Now, can we add to the list, can we add ji? Well, ji will commute with H0. Again, because it's Li plus Si, and Li and Si are 0. Ji with Ls, well, do it the same way as here. Ji with this thing, well, Ji commutes with j squared, because that's the Casimir for j's, and Ji commutes with L squared, because L squared commutes with anything built of L and S, commutes with S squared. So this is also 0. So we can introduce a ji. Ji commutes with H prime, commutes with L squared, S squared, J squared. So we can put a ji, but as you know, you can only put one of them, because once you put, say, the jz, you cannot put jx or jy. So jz is here. And that's it. This is our set of commuting observables. Is a complete set of commuting observables, and we should expect that we can diagonalize all of them simultaneously, because they commute and they're Hermitian operators, and therefore our theorem guarantees that, which means we will be able to find energy eigenstates in principle of the total Hamiltonian by diagonalizing this. But while we won't find exact energy eigenstates of the total Hamiltonian, we will find approximate eigenstates in the Feynman-Hellman way by diagonalizing j squared and jz. Because j squared is the same thing at L dot S, and L dot S is a key part of the matrix perturbation. So if we manage to diagonalize j squared, we've diagonalized L dot S, and therefore we've solved our problem. So our next task will therefore be to examine how to construct eigenstates of j squared.